Hello, I am Weiyu Zhao from Harbin Institute of Technology. In this video, I will present an overview of our work submitted to the GENEA Challenge 2023. In this challenge, our paper is titled DiffuGesture, Generating Human Gesture from Two-Person Dialogue with Diffusion Models. We aim to address the task of gesture generation in dual-person dialogues using diffusion models. This work was a collaboration with Dr. Liangxiao Hu and Professor Shengping Zhang. For this challenge, we expect to construct a multi-modal-driven co-speech gesture generation system. Unlike the previous GENEA challenge, we will pay closer attention to dyadic scenarios. Furthermore, in order to establish a one-to-many mapping relationship between speech and gestures, we will attempt to address the gesture generation problem using probabilistic generative models different from LSTM, RNN, etc. Additionally, we aim to ensure high-quality gesture generation as much as possible. The system is divided into 3 stages, including the pre-processing stage, training stage, and sampling stage. We ensure the continuity of movements by taking the interlocutor's behavior, speech, speaker ID, and transcription text as inputs, and use the previous pose as a seed pose. Through classifier-free guidance, we train a cross-modal transformer encoder to progressively remove noise and obtain high-fidelity main-agent action sequences. In the pre-processing stage, we utilize various dataset information such as audio recordings, transcribed text exchanges, and speaker identification. Our pre-processing approach aligns with the baseline method, involving the processing of audio, text, and human body joint data. We extract 3 audio features, MEL spectrograms, MFCCs, and prosodies, and generate motion frames at 30 frames per second, aligning with the motion sequence durations. Textual information is encoded using fast text, resulting in word vectors of dimension 300. Speaker identities are represented using one-hot encoding. For the motion data, we select 25 key joints, including the root node, which significantly influence skeleton motion. We segment the motion sequences into 300 frame chunks, which served as inputs to the diffusion process. After aligning audio features, encoded text, speaker motion sequences, and identity information in the temporal dimension, we pass them as inputs through a conditional encoder. Simultaneously, to ensure smooth continuity between adjacent motion segments, we include the preceding 50 previous poses as seed poses, processed through a prepose encoder. The outputs of both encoders are concatenated to obtain the input conditional data, denoted as C. Generating 3D gesture poses using conditional diffusion models is different from generating images. Both the pose sequence X and the multimodal conditions exhibit strong temporal dependencies. Here, we need to establish a module to ensure that our results are time-dependent. We employ a lightweight transformer encoder to encode frames of continuous motions and multimodal data. We align the noisy gesture sequence and multimodal conditions in the time dimension and treat each frame as a separate token, and the time step is treated as a separate token. Generating motion from speech is an implicit mapping rather than a direct one-to-one correspondence between speech and gestures. To ensure a better correlation between audio and actions, we introduce classifier-free guidance. We achieve this by randomly masking the multimodal condition data. And we alternately train the transformer encoder and MLP layers in both the conditioned and unconditioned scenarios using the same set of parameters. Ultimately, we use a hyperparameter, S, to balance the diversity and quality of the outputs. This approach allows us to achieve classifier-free guidance. In the sampling stage, we demonstrate the process of starting with random noise and generating a clean sample through denoising steps. Here, we showcase some of our results. The first 3 segments include only the gestures of the main agent gesture, while the 4th segment is a complete dual-person dialogue.
So there's 7 of us, and we have like this room that has 2 like queen or full beds, and then like 2 like day beds like out in the living room.
You won't converge, and you need to have someone to push you towards some direction that you start to really dive deeper. No, we're going to do it, and then he still takes the burden to drive to the university to do it with us. I mean, that's interesting, but
Okay.
Now there's only 1 skull person left,
Okay.
right? And so this guy,
Which one is he?
he's the
Okay.
you can't really tell with him, but like I think he's the leader. And
According to the results of crowdsourced voting, Our system, SB, achieved a moderate score in appropriateness for agent speech in the bar chart, while it obtained a gratifying score in appropriateness for the interlocutor indicator. Based on these results, we believe that our approach to handling multimodal data is effective. Furthermore, the diffusion model proves to be successful in ensuring the generation of main agent gestures in specific scenarios. However, our score on the human likeness indicator is not satisfactory, as we only scored 24. Based on the assessment results above and our subjective observations, we will now discuss the limitations in our system. Firstly, it's important to acknowledge that the motion sequences provided for evaluation may not have been in their final or optimized form. This suggests that we might not have fine-tuned our parameters to their most suitable settings. Next, this challenge presented us with long-term human gesture sequences of variable lengths, which posed a significant challenge for our approach. Our initial approach relied on naive diffusion models that were not specifically designed to handle variable length sequences. We attempted to address this by segmenting the condition sequences and predicting 300 frames for each segment, concatenating these fixed-length motion sequences to generate complete motions. Unfortunately, this approach led to noticeable jitter at the junctions of the predicted fixed-length motion sequences. In our efforts to mitigate this issue, we explored incorporating previously predicted motions in the acceleration between adjacent frames as part of the conditions. Additionally, we increased the length of the generated sequences to reduce discontinuities in the generated motions. However, these naive methods did not yield the expected results. The acceleration constraint, in particular, limited the richness and natural. In our upcoming work, we will strive to improve our system to generate higher quality gesture sequences. In conclusion, thank you for your attention.